Okay, this is the first video for chapter 31, which concerns electromagnetic induction. We're going to be looking at Faraday's law. What Faraday's law is about is a changing magnetic field can create an electric field, and if that electric field is created in a conductor, it will produce an electric current. So that's what we mean by induced fields and induced currents. There's some things you notice, like for instance, if you take a loop of wire and you take a bar magnet, north and south, and the field lines point from north to south, about like that. If you move the magnet toward or away from the loop of wire, what we notice is that current flows around the wire. And the way that's typically explained is that if the number of field lines through that loop changes, an EMF will be induced. And remember, number of field lines through the loop, that is the magnetic flux. What Faraday's law says is that E equals N times the time derivative of the magnetic flux, where N is the number of loops of wire. In the picture I drew, there is N equals 1. There's only a single loop. If you were to loop it 5 times around, N would equal 5. And that EMF is basically a voltage. There's some mathematical differences, but you can think of it as a voltage. The current that is induced in the loop would be that voltage divided by the resistance of the loop. And magnetic flux is a lot like electric flux. It's the number of field lines that go through a surface. The difference is that the surface will not be closed the way it is when we use Gauss's law. And quantitatively, it's much the same thing. If the magnetic field is uniform, meaning the same everywhere, the magnetic flux equals B dot dA, where the area vector is defined in the same way we defined it when we were talking about electric flux, meaning as perpendicular to the surface. And that means that if the magnetic field points like that, and that angle's theta, becomes B times A times cosine theta, or B times dA times cosine theta. But if the magnetic field is not uniform, which is the case in most of the interesting problems, you have to integrate. You have to do a Riemann sum. So the idea is you have a potentially curved surface that you break up into a lot of very small dAs, and the magnetic field has particular values at each of those dAs. You add all of them up to get the total flux. Most of the time in this class, we're going to be looking at cases where the magnetic field is constant or uniform over the area we're dealing with. But there is one problem in your homework assignment where it's not, and we'll look at I'll give you some tips for that at the end of this video. Now, Faraday's law, which I already wrote down, but I will write down again, says that the induced EMF equals N times d phi dt, where phi is the magnetic flux through the loop. And our example, which is part A of problem 3 in your textbook, shows a loop with a magnetic flux through it, and the loop has a resistance in it, and the field points out of the page. And we're told that the flux increases according to the equation 6t squared plus 7t. We're also told, though I didn't write it down, that phi is in milliwebers, and that brings us to the next thing, which is the units of flux which is the Weber. And a Weber is equal to a Tesla times a square meter. So phi is in milliwebers. There's only a single loop here. So the EMF is just the time derivative of 6t squared plus 7t, which is extremely easy to do. 12t plus 7. And at 2 seconds, that equals 19. And because our units of flux are milliwebers, that means our units of EMF will be millivolts. Because a Weber times Webers per second is a volt. So very straightforward example there. That's the kind of thing you'll see in the early parts of the assignment. The second law that goes along with Faraday's law is something called Lenz's law. This tells you what the direction of the induced current will be, because Faraday's law doesn't tell us that, it just tells us what the magnitude is. And the idea with Lenz's law is conservation of energy. The induced current will produce its own field, and that's just because electric currents produce magnetic fields. And the field created by that induced current will oppose the change in flux. If it didn't do that, you would have the potential for positive feedback, and you'd violate conservation of energy. So the way you figure this out, and this is probably the easiest way I've found to evaluate Lenz's law, is that you take your right hand, you point your right thumb in the direction of the field through the loop. Then you ask the question, is the flux increasing or is the flux decreasing? If the flux is decreasing, the induced current will flow in the same direction as your fingers curl. If the flux is increasing, the induced current flows the opposite direction. So in problem 3b, you've got your loop of wire, and you've got your magnetic field pointing out of the page, and because the equation is phi equals 6t squared plus 7t, we notice that its derivative is positive everywhere, so the flux is increasing. That means that we point our thumb out of the page along the electric field, and that means that the fingers go counterclockwise. But since phi is increasing, the current flows opposite that, and it goes clockwise. And that answers 3b, which wanted to know the direction of the current around the loop. So you've got Faraday's law, which says the induced EMF is equal to the rate of change of the flux, and you've got Lenz's law, which tells you how to get the direction of that induced current. Now, problem 21 is a slightly tricky problem that asks you to find the flux through a loop where the field is not uniform over the entire loop. It's a rectangular loop. I don't know. I think the dimension, I'll just call this dimension A, although I'm not sure if that's how the problem defines it. But the field is given as a function of y. So y is vertical direction, x is horizontal direction. It doesn't vary with x, just with y and t. And so what you'll do is your dA, remember phi is equal to the integral of b dot dA, your dA will be a long, narrow strip of it that equals the width of the loop times dy. And so this becomes A times b dot dy, and you'll integrate from the bottom edge of the loop to the top edge of the loop. Now b is also a function of t. For the purpose of this integral, t is a constant. you don't use, and then when you take the derivative, it will be with respect to t. So it's kind of good practice on relatively simple multivariable calculus, which really isn't as hard as you think it is. For tomorrow, I'm going to check questions 1 through 4. Please do work on problem 21 as well. We'll talk about it in class.